All right. So, any questions about the quiz here? It is kind of a funny thing where it doesn't matter. I mean, I just pulled this number out of the sky, right, when I sat down. It seems like it's so common that I'll pull numbers out that go the same way forwards and backwards. It just happens to be this random thing. But do understand when we wrote our result, this one right here, this far left one, is this one right here. This far right one is this one up here. I'll turn in a ticket for this. There's something. Can't tell if it's like a loose connection or it might just be the panel. Yeah, it's been not good. Okay. So let's keep trucking from last time. Let's see, we were up here. So here's where you learn to do the different conversions stuff. We looked at decimal to octal. We saw that it's the exact same pattern. Divide by 8 instead of divide by 2. You'll find that the same thing's true if we go from octal to decimal. So for instance, the number 102 octal. To decimal. This is the ones place, the eights place, the 64's place. Or you can think of it as this is 8 to the zeros place, 8 to the ones place, 8 to the twos place. Do the exact same math. So this is 1 times 64 plus 0 times 8 plus 2 times 1. And that is a 66, which you'll see is that's the number we started with right here. All right, so it's the identical pattern whether we're going from octal or binary or hexadecimal. Hexadecimal has a little bit of a catch here. Let me show you that. All right, so let's say that we want to go from 2589 decimal to hex, which is base 16. All right, so our common bases for computers are base 2, base 8, base 16. All right, and when you take computer organization, you'll understand why that's very common. But just trust me for right now that it is. All right, but for humans, we like base 10. So we operate in this number system here. All right, so to convert from decimal into another base, we do that divide over and over again thing, right? So this is 2589 divided by 16. It'll just pop back up, just deal. All right, so 2589 divided by 16 is 161. All right, 161 times 16 gets me 2576. So that's a remainder of 13. $161 divided by 2 is 80. I'm sorry, not divided by 2, divided by 16. 161 divided by 16 is 10. 10 times 16 is with a remainder of 1. And then 10 divided by 16 is 0. 0 times 16 is 0 with a remainder of 10. Now, based on what we know so far, we read our answer from bottom up. So this is 10, 1, 13. Okay, well, that's weird right off the bat. when we read it from bottom up, each of these has to represent a single character. All right. In hex, so if we, let me just go back and create a extra slide here. So we're going to say language of bases. So binary has a language of 0 and 1. Octal has a language of 0, 1, 2, 3, 4, 5, 6, and 7. Decimal has a language of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Hex has a language of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, and F. I really wanted those to be all caps. Like that. All right, so that's the language of hexadecimal. So after a 9, a 10 is an A, an 11 is a B, a 12 is a C, a 13 is a D, a 14 is an E, a 15 is an F. All right, so the possible hextets is what they're called of hexadecimal is 0 through 15. 0 through the base minus 1, just like with decimal, our base is 10, 0 to 9 is our numbers. Octal, base is 8, 0 to 7 are the numbers. Binary, base is 2, 0 to 1 are the numbers. So for hex, 0 to 15 are the numbers, but the 10 through 15 we represent using letters. So now when we come back in here, we actually need to map this 13 to a D. The 1 stays a 1. The 10 gets mapped to an A. So this is actually the hexadecimal number A1D. That make sense? All right, and you can take this all the way up to base 37. So that would be 0 to 9, A through Z. Would be the, after that we run out of alphabet. So you know, one theory is you might switch over to Klingon, but we've looked it up. There's actually only 22 characters in the Klingon alphabet, so that won't help. You probably could go to like the kanji alphabet, but not new style, but original, where you have a bunch of symbols, Chinese symbols for a zillion different things. Yeah, then you'd have unique representations for all the numbers. Nobody does that. Okay, right now, base 37 is as far as we go, but in practice, we actually only go up to base 16. All right, now, this 2589, let's take this same number and let's make that guy, let's make it octal. So we divide. I'm actually just going to do it with Google real quick. 2589 decimal to octal. That's 5035. So we'll say 5035 in octal. Then let's do it to binary. Is there no button to make it happen? So this is going to be a scary binary number. All right, so this is hexadecimal, this is octal, this is binary. What's the advantage of going to higher bases? What's the advantage of base 16 versus base 2? Or what's one advantage?
That there's only 3 characters in hexadecimal orders.
Yeah. So, human beings like this number. This number is meaningful to us because we're used to the base 10 counting system, right? Okay. Now, is this number here the same number as this one? Yeah, it's just encoded in binary, right? Is this number here the same number as this one? Sure. Is this number the same number as this one? They're all the same. We can move between those bases, right? So when we have a very, very, very large value, it might make sense for us to encode that value in a higher base for footprint reasons. Does that make sense? A base 16 number is going to be smaller or no larger than the equivalent decimal number. And what I mean by that, like the number 1 in decimal is the number 1 in hex as well. They're both the number 1. All right. So another interesting. So we understand that doesn't matter what base we're working with. We're still representing the same underlying mathematical number. Okay. We just like the base 10s because 10 fingers, 10 toes, that stuff. All right. So this is a fun one. $25.89 from decimal to decimal. Okay, now, right off the bat, you might say, well, why would I ever do that? Right? The answer is $25.89. Right? I'm converting it from itself to itself. But just to prove that the pattern is identical, we're going to go through the motions. $25.89 divided by 10 gives us 258. Remainder 9. 258 divided by 10 gives us 25. Remainder 8. 25 divided by 10 gives us 2. Remainder 5. 2 divided by 10 gives us 0. Remainder 2. Reader answer from bottom up, 2589. Okay. Identical pattern. Doesn't matter what base we're working with. There aren't any special cases. Okay. The only thing we need to be concerned about is the language of the base that we're going to. That is, if it's a base greater than base 10, you're going to have to do some conversion to letters instead of the decimal, instead of the digits. Because we can only go up to 0 to 9. After that, we go into the alphabet. All right, that makes sense? Now, when we go back the other direction, for example, if I have A1D from hex to decimal, we use the other pattern. So this is an A, this is a 1, this is a D, this is the 1's place, this is the 16's place, this is the, 4096? No, 256. This is 256 place, this is the 16's place, this is the 1's place. Now, an A is actually, let's go the other direction. This is actually a 10. This is actually a 1. This is actually a 13. So now 256 times 10, 2, 5, plus 16 times 1 plus 1 times 13 is 2589. So that's converting it back to decimal. See how that worked? So if I'm going from hex, or really any base above base 10, so base 11 on up, fair game in here from this point forward is I should be able to ask you to convert any base from base 2 to base 37. They're all fair game because it's all the same model, right? So base 11, the legal, I don't even know what the name would be called, the legal digits in quotes, let's say, would be 0 to 9 and an A. That would be base 11. Base 12, 0 to 9, A and B. Base 16, 0 to 9, A through F. Base 37, 0 to 9, A through Z. Go ahead.
So A is represented by the 10, but why is it 256?
Yep, same reason as we had in binary. This is 16 to the 2. This is 16 to the 1. This is 16 to the 0. When we were doing binary, this was 2 to the 0, 2 to the 1, 2 to the 2. Make sense? So the far right one will always be a 1. So anything to the 0 power is a 1. Then you multiply it by 16, multiply it by 16, multiply it by 16. Keep going as you're going to the left. All right? That makes sense? So there's 3 skills you need. Well, besides just being able to multiply and add. We're assuming you came to class with that, right? Okay. 3 skills. 1, you need to know the pattern when you go from decimal to a base. The other one, you need to know the pattern when you go from any base to decimal. Okay, 2 separate patterns, right? Decimal to a base, we do the divide thing, record the remainder. Base to decimal, we do the place thing, the ones place times the base times the base times the base, and add it all up. And then the third skill we need to know is that a 10 is an A, an 11 is a B, a 12 is a C, so on and so forth. That make sense? All right. So with those 3 skills, we now can count in any base. We now can convert from any base to any base. Why do you think hexadecimal is a popular base for computers? Go ahead.
You can write a lot with a little compared to like binary.
Okay, so this comes back to our idea of having bigger numbers represented in smaller footprints. Why is that important in computers? Go ahead.
Faster processing.
Let's say no. There's probably some sort of weird, crazy 64-bit argument or something like that where you might be able to prove there's 1% truth in that, but big picture.
Saving space in memory.
Even that's not necessarily true because we're still storing stuff as zeros and ones. Yeah, so when we see them, we're seeing them in hex, but we're actually still representing them in zeros and ones. Although, I'll give you the benefit of the doubt. Your answer is probably more right than his answer. We'll give him a 1%. You can probably make a 7% argument on yours. Because there is some situations where you could save some space if instead of storing the value in binary, you can store like A1D as the binary 10, followed by the binary 1, followed by the binary D, binary 13. And tactically, base 16, you can represent in 4 bits. It's called a nibble. Don't write any of this down. We learned about this in 325 in depth when we write assembly code stuff. But then you could actually represent a 3 hextet base 16 numbers in a maximum of 12 bits. 4 bits for each of the hextets. 0 to 15 can be represented with 4 bits. When we think about our computers today, What is big? So when you get your computer and you're rattling off the specs of your computer to somebody, and you talk about that, okay, well this is I have this, and this. What are the things that have large numbers associated with it based on what we learned recently? Memory. Okay, so we could say RAM. We mentioned how much RAM do we have in our computers today? 4, 8, 16 gigs. All right, so let's just say we have 8 gigabytes of RAM. Actually, if you're buying a computer today, you probably have 16, realistically. Especially if you're going to brag about it, right? If you get the new computer and you have 4 gigs of RAM, you're probably not telling your buddies. All right, so we're going to say we have 16 gigs of RAM, okay? And we know that 16 gigabytes is how many bits? So this is 16 times 8 times 1024 gets us megabytes, times 1024 gets us kilobytes, times 1024 gets us, megabits, kilobits, bits. So this is the number of bits. Oop. I did a better job than that, I promise. That's the number of bits in 16 gigabits. Big number?
Yes.
Okay. What else is big in our computers? Storage. So let's make it look extra scary. So we'll talk about the HDD rather than the SSD. So what's the difference between an HDD and an SSD? Besides cost.
The HDD has like a moving disk.
Yeah. So HDDs, these are mechanical hard drives. And a lot of times, you'll see like a 1 or a 2 terabyte mechanical hard drive in a machine. Way slower. Orders of magnitude slower. So if you ever have the opportunity to upgrade a computer from 1 terabyte HDD to 128 gigabytes, significantly smaller, SSD, do it. The first upgrade in your computer you will feel the performance difference is the hard drive. Really, really, really common oversight by computer users. Almost always you'll look at these, say, well, why would I get 128 gigs or 256 gigs when I can have a terabyte, which is obviously huge because most consumers don't even know. Just terabyte just sounds like a monster compared to gigabytes, right? You will be far less happy with the performance of your machine. That's why Macintosh computers, laptops have felt so fast for so long compared to their lower priced competitors. It's not that Apple's worth the price now, let's say, because now everybody has solid state drives in there, but Apple was offering high speed solid state drives before everybody else was because Apple just said, look, our crap's expensive, so we don't care. You want a Mac laptop? It's $3,500. Comes with a solid state drive. Great, super fast, but it's $3,500. Where before that was like common knowledge, you might go out and buy an HP and say, I'm not paying $3,500 for a Hewlett-Packard laptop, especially since it's made of plastic rather than titanium carved out of some mountain. Yeah, go ahead.
So 124 gigabytes is actually faster than 1 terabyte, but isn't 1 terabyte 1,024 gigabytes?
We're talking size versus speed. So we might say a 1 terabyte, or this is a 1024 gigabyte drive versus a solid state drive, which let's say is 128 gigabytes. This guy is faster than this guy. He holds less crap. 128 is smaller than 1024. So it can't hold as much, but it's way faster. Okay, and I can't emphasize enough how much faster solid state drives are. It's orders of magnitude faster. We're not talking about double or triple the speed. Hundreds of times the speed. Way faster. It'll be the first thing you notice. If you have an aging desktop computer or a laptop that you can swap out the hard drive on, that is not a Mac, or not a Mac and a, I don't know, guts. Any more Apple computers are either made as a solid piece or they just use so much glue. When you buy the computer, just spend top dollar day one, and because you want to have everything in it that you'll ever need. Nothing's replaceable inside these machines. So this Mac here, the hard drive is not a traditional hard drive, solid state drive. It's a soldered on solid state chip. Processor's a chip. RAM's a chip. There's nothing replaceable in there. Why not? Why do you think Apple makes their products with everything soldered onto a single board so it's not replaceable?
So instead of upgrading your current one, buy the new one.
Okay, so that's the evil business mindset. That I'm going to argue that is the happy accident that comes from the real reason.
Well, I would say two things. It's smaller, so they can put it into a smaller case, and it's faster.
Okay. That's probably still true. Faster is probably still true because you aren't going through as many interfaces. So I'll say it is probably faster. One thing when you look at Apple stuff, Apple's all about design, right? So you get smaller cases, so everything's super sleek to the point where you can chop vegetables with a MacBook Air. You can sharpen that edge on the end of it, put it in. You actually can. I've seen somebody do it. You have that, and then also something else. I mean, we always like to demonize the big companies. Microsoft was demonized for years and years and years. Interesting thing, Microsoft's making a comeback. They're becoming cool again. It's kind of an interesting thing. That'll come back up as semester goes on. But, Apple's been demonized for a long time, but I guarantee you Apple had crazy sounding battery life on their laptops way before anybody else did. Right? Apple was saying, hey, our laptop will last 10 hours, 12 hours, 14 hours, whatever it is. Why? Because everything inside of this is battery. I got this little tiny, everything's on a single board up here at the top. And then the whole rest of the insides of this is battery. And it's not even a replaceable battery. Why isn't it a replaceable battery? Because the components that it would take to, lock the battery in and be able to make it replace, that takes up space that could be more battery. That make sense?
Yeah.
So Apple can make the argument that, hey, we're making your life better and more expensive.
Yeah.
So it's a trade-off, right? I mean, you'd be hard-pressed to, I would probably say you couldn't buy a laptop today that is the same dimensions as a MacBook Pro that has the speed or battery life of a MacBook Pro. And Apple's using the same parts as the other companies. It has an Intel processor in it, just like that has an Intel processor in it. Okay, maybe do you have an AMD? It was a coin flip. There was a 90%. What an Intel compatible processor. Yeah, Apple won't use AMD because they're junk. No, they're actually fine. So in any case, they use the same parts. Samsung makes the RAM for half these computers, which is funny because then you have these interesting situations where Apple's sues Samsung and Samsung's making the displays and the RAM for Apple parts. Yeah, it's all very interesting where you have, because these companies have become so large now where they have different silos. Where I was involved in a situation, this is 15 years ago, something like that, 16 years ago, maybe even a little more than that, where Verizon sued themselves.
What?
So this is when I was teaching at Western Illinois University, which is in a little podunk town. It's in Macomb, Illinois. And this is in the very early days of high-speed internet. And, big cities would have high-speed internet by then, but, in Macomb, we had nothing. So you had these local internet service providers that would offer DSL at some crazy price, right? Because when Verizon sells the telephone circuit for a DSL connection, they sell it to you based on the number of subscribers you have. So our local internet company was able to sell us, 1.5 megabit per second high-speed connections, which was fast back then, for $300 a month or something like that, because you were paying for their circuit fee. Well, then all of a sudden, after they had that for several years, they had an agreement with Verizon that they would be the only show in town. So then what happened is Verizon Online, which is another subsidiary of Verizon, it's a separate, another silo. That's their internet service provider division. And they can claim all the Verizon customers on the planet. So they could get the cost of those same circuits down to a fraction of what our local provider was paying. So we started getting these flyers in the mail that, oh, we can get the same internet connection that we had for like $21 a month instead of $300, right? And it wasn't even the local internet provider's fault. I mean, we're hardly making money on this. Yeah, so what ended up happening is because the local providers had an arrangement with Verizon, together they sued Verizon Online. Is that funny? So what ended up happening is Verizon Online never came into town, but then all of a sudden, you know, so this all happened at the same time, so you didn't have a two-step thing here. Because what would happen? Let's say you were in that situation. You're currently paying $300 a month, and you could be paying $25 a month. I think it was 22 something, but $25 a month. And then all of a sudden the lawsuit goes through and says, okay, we won't let the cheaper one come into town. You can just keep paying your $300 a month. We're humans. You know, that local provider, that mom and pop shop that we go to church with, they can just go out of business. We don't care. we don't. So what ended up happening is they were able to get the circuits for the same price as Verizon Online did. So we were able to support the local provider and pay $25 a month, and it all worked out. But funny situations like that where sometimes you have companies who sue themselves. Or the Microsoft way, if you want to bash on Microsoft in our last minute. And this is actually all big company policies pretty much. You know, you've heard stories of these big companies stealing technology from other companies. So let's say you're a software developer and you come out with some really cool technology and, you know, you wrote it in your underwear in your grandma's basement or something like that. And then Microsoft comes and steals it from you. All right. And then you sue Microsoft, right? And very rarely do those things go to court. What happens? Does Microsoft just settles outside of court with you? They say, here's $1 million, here's $12 million, whatever it's actually worth to them. What do? You're all upset. Well, Microsoft turned around and made $25 billion from that. Well, they have a huge marketing engine behind it. You wouldn't have made $25 billion on it. You don't have pants on. So, but that's a lot of times the MO of the big companies. Instead of doing an acquisition where they'll buy something or go through the normal legal channels of, you know, meeting with you to buy the product, they'll just steal it, let you get ticked off, settle with you outside of court by writing a check, and they were able to go to market quicker and probably save some money. It's the world we live in.
You have to sell it, and like in the fine print, 1% of all future profits you make from this.
Yeah, Microsoft doesn't do that. That's a similar story recently. Was, and this is completely outside of technology, but there was a recent golf tournament player, Matt Kuchar, pretty good player, and his normal caddy couldn't work that week, so he hired like a local person from the like area who knew the golf course really well, and he won the tournament. And typically, the arrangement between players and their actual caddies are the caddies have like a weekly fee and they get paid, and then they make 10% of the earnings of the player. Well, so Kuchar made up $1.5 million. So you're thinking this guy should get $150,000. He got a check for $5,000 because that was the arrangement that he made because he wasn't his normal caddy. But now, you know, now this guy's all over the internet and stuff like that saying, "Where's my cut?" Yeah. But okay, so probably the next section of the book, I'll take a look here after class. Probably not a quiz next class. Always a threat of a quiz, but I'll say there's unlikely a chance of a quiz. And I want to power through this. We've done most of this stuff. And then let's start getting into programming next class. Cool?
I understand this now.
All right, good.
Yeah, I have a quick question.
Here, let me stop the recording real quick before I